C'est sûr? Mais on attend encore 2 minutes pour voir s'il y a des autres gens qui viennent ou on commence?
Non, on peut commencer.
On peut commencer?
Oui.
On attend au moins que Jean-Claude rentre. So Giovanni, ça va?
Hey, I'm good. Good to go.
Are good? Okay. So, Enrique. So welcome back to the afternoon session. The first speaker of this afternoon is Giovanni Conforti, and he's going to talk about Hamilton-Jacobi equations for controlled gradient flows, the comparison principle. So Giovanni.
Okay. So thank you very much, Luca, for the kind introduction, and also a great thank to the organizer who managed for people to be present even online. So what I'm gonna talk a bit about today is the uniqueness problem for a class of Hamilton-Jacobi equation that is tightly related to the Schrödinger problem, as I'm going to explain in a second. So I've been thinking about this for a while now, together with Richard Kraaij, I think it's the right pronunciation, from the Netherlands. This is Delft. And together with Daniela Tonon, formerly in Paris, currently in the beautiful town of Padova. Okay, so first of all, I would like to motivate a little bit why the class of equations I'll be looking at are interesting for somebody who is passionate about the Schrödinger problem. And I would like to start from the framework that you've already encountered in Luca's talk. So I consider this kind of abstract version of the dynamic Schrödinger problem that is set on a rather general metric space. So I'm sure you have already seen this during this conference, but let me just recall what it is. So we give ourselves a metric space, complete one. And the problem we consider is that of minimizing among all absolutely continuous curve that start at a given nu, at end at a given nu, a dynamic cost, which is composed of two parts. We have a kinetic part, which is the metric speed of the curve, plus we have a part, which is the slope of a certain energy function. So the proper definition of the metric slope is it's given here. So it's a proxy for the norm of the gradient of the energy. But of course, in general, this gradient does not really exist. But it's good to keep this analogy in mind. Okay, so this framework is pretty abstract. Just to give a couple of examples. Well, if E is just relative entropy, and of course the space is the space of probability measures with second moments, then we recover the superclassical Schrödinger problem. If we add some interaction term, then we recover the mean field version of the Schrödinger problem. But there's plenty of examples. So this is exactly the framework that Luca, Leonard, and Dimitri have studied. Actually, I would like to rewrite this problem in a formally equivalent way. I would like to rewrite it as a controlled gradient flow problem. I think Enrique has even hinted at this change of variable in his talk. So essentially, I do the following thing. Now I put myself in a slightly less general setting. So I suppose that instead of having just a metric space, I have a Riemannian manifold. And my curve gamma, I interpret it as a correction of the gradient flow. So what do I mean by that? instead of, so the velocity of gamma is made of two parts. There is one part, which is just the gradient flow, and another part, which is a correction that I applied to the gradient flow. And my objective now is to steer my particle system, or I mean, steer my gamma from mu to nu in such a way that the resulting curve is applies the smallest correction possible to the gradient flow. So I have to go from one way to the other, and I have to try to be as close as possible, as close as I can to the gradient flow. So once again, at least at the formal level, the two problems are essentially the same problem. There are some boundary terms that I've not written here that depends only on mu and nu, but they don't influence the, I mean, they don't have any role in determining the minimizer. They just change a little bit the cost. So why did I choose to work with this formulation instead that working with the other formulation? Is that this one is more amenable to the usual Hamilton-Jacobi business, because now we really have a control problem. And as you are well aware of, Hamilton-Jacobi equation often arise in connection with control problems. So we have control problems, of course, on a very general space. But still, it's not any control problem, so it's a control gradient flow problem. So the motivation that we had is, okay, now take this abstract version of the Schrödinger problem. What is the Morse-Kantorowicz duality for this one? So for this problem, quite recently, Luca, Leonard, and Dimitri have established quite a number of general results that extend what is known for the classical Schrödinger problem or for optimal transport. And here we are after another generalization of classical results is Morse-Kantorowicz duality. Okay, so of course there's one thing that is probably worth mentioning, that this problem here does not necessarily admit a static counterpart. So it's really a dynamical problem. So we will have to look for these duality results. We will have to look at a dynamical duality result. This is already available for the classical Schrödinger problem through the standard Hamilton-Jacobi-Bellman equation. And now, in order to tackle this more general problem, we somehow have to move from RD to the space of probability measures of the RD in order to write a proper duality result. So let me tell you how you can do this. You can answer completely my question very quickly and very formally. You do exactly what people do in control. So you define, you pick a Lagrange multiplier phi, and you include it in the cost function. So you include a terminal cost in the Schrödinger cost function, and you remove the hard constraint that you had terminal time. So this constraint that was there before, you just kill it. Then you fabricate a new problem, which I called relaxed Schrödinger problem. And as a last tweak, you allow yourself to start from any little t that is smaller or equal than capital T, which is the time horizon over which you look at the Schrödinger problem. So you define the optimal value of this modified problem. You call it V phi Tx. Sorry, X is a typo. It's T. So in control, people call this actually the value function of the problem. And if you believe in the dynamic programming principle approach, then you will find that at least at the formal level, this function V phi T mu satisfies the following Hamilton-Jacobi equation. So you have boundary conditions at the terminal time. Okay, And then the interesting part is the dynamical part. So we have that the derivative in time of the value function minus 1/2 the gradient of the value function squared. So this is the usual part coming from the kinetic part in the cost, minus another term, which is really specific to Schrödinger, which is the inner product between the gradient of the energy times the value function. This whole thing has to be equal to 0. So it's really easy to get this equation from this control problem. You just reduce everything to a toy model in RD. This will be exactly the equation that you get by doing the standard control on RD. And the formal answer that it is once again very easy to see in RD is that the cost is obtained as the supremum of the difference among over Lagrange multipliers of the difference between the value function at 0 evaluated at mu and the Lagrange multiplier evaluated at mu. So this is very general, very formal result. Now the problem is that this equation is as it is written doesn't make any sense. Of course, the gradient of the energy does not exist in general, and even if it exists, you don't really know whether or not the function v is differentiable. So the problem that you face if you want to write down a proper duality result is that of giving a proper meaning to this equation. Sorry, here there is another typo. Here there is also a gradient, of course. But I'll come back to the equation later. Okay, so that's what we were about. And just to give a little bit of background, so this equation here is an Hamilton-Jacobi equation on a metric on a general metric space, and it relates pretty much to the Hamilton-Jacobi equations that you encounter in what probabilists call Mekin-Vlasov control. And it's not so far from what people in mean-field game look at, namely the so-called master equation. Not so far and not so close, in the sense that the master equation is not by itself issued by a control problem, but still there are quite some analogies. The big difference is the structure of the equation. Namely, in those equations here, you typically don't encounter this term. You may have other terms which are even more complicated than this one, but you don't have this inner product between the gradients. Okay, so the rest of my talk, I will try to motivate a little bit the study of an equation which is closely related to this one, but not exactly this one. And to give you some ideas on how we defined the notion of viscosity solution for this equation. And what is quite interesting is that the way you define viscosity solution is through some fundamental objects of optimal transport, like EVI inequalities and gradient flows. So I'll come to that later. But okay, I hope it's clear. What we are trying to do is duality for this general version of the Schrödinger problem. Okay, let's come to the Hamilton-Jacobi equation that we actually consider. It is also related to a control gradient flow problem. So essentially, it's the same problem as before, up to a sign change that it's really harmless. So it's this red one. If I minimize this functional here, then I'm just looking at the same equation I had before. But then in order to get rid of the time variable, I consider an ergodic version of the problem. So I integrate over capital T. So this is not something that, at least, I mean, it should not be something really deep. We are just using a trick to get rid of the time variable and to reduce ourselves to an ergodic control problem. So the difficulties in solving the equation coming from this problem should be the exact same difficulties that you encounter if you were to solve the equation for the other problem, the one I've just shown you. But why did we choose to work with this equation? There is a reason, is that the equation that comes from this problem is, well, I wouldn't say very well, but it's quite studied in the literature. Namely, it's studied by people doing statistical mechanics, because if you're able to solve the equation that comes from here, then you can prove a large deviation principle for interacting particle systems. So this whole technology has been developed by Jin Feng and his co-authors in a series of works. Here I just put like the first one I'm aware of and the last one I'm aware of. So let's have a look at the equation that, once again, through the dynamic programming approach, comes out of this variational problem here. It's the following one. So instead of having a time derivative, we just have f. So we don't have the time derivative anymore. So we have f minus some Hamiltonian applied to f, it's equal to phi. Phi is the Lagrange multiplier. And the Hamiltonian applied to f is exactly the object that we have encountered before. So we have formally 1/2, the norm of the gradient of f squared, minus the inner product between the gradient of f and the gradient of our energy function. So with respect to the equation that I showed you before, I have keyed the dt part because I integrated over time here. And the phi before was only in the boundary condition, you see, and now it has become part of the equation. This is once again because I have integrated over time. But somehow the core of the difficulties, which is this, the form of the Hamiltonian, has remained the same. So if you look at the papers that deal with this equation from the large deviation standpoint, they do a lot of things, very interesting. But when we look with the eyes of somebody interested in the Schrödinger problem, they are not. So those results, they do not even cover this equation when E is the classical relative entropy, and the metric space is a space of probability measures over RD. So in other words, it doesn't even cover the Schrödinger problem for independent Brownian particles. And the reason why it doesn't cover this problem, the reasons, actually, there are several ones, are very technical, and I wouldn't like to go too much into detail here, but I'll probably give some hints on why even those simple cases can be difficult. Almost at the end of my talk, I'll do that. But okay, so this now, from now on, I think the message is that we try to solve this equation in a general setting, and this equation is a proxy for the equation that appears in the formal duality result for the metric Schrödinger problem. So this equation has the same problem as before, is that the Hamiltonian is actually ill-defined. So even if your f is Lipschitz, in general, you cannot really make sense of the gradient of the energy. So even writing this Hamiltonian down is a problem. So we first have to understand how to modify the Hamiltonian in order to get a meaningful object. So let me now present you a first attempt to come up with a rigorous notion of viscosity solution. So the idea, that is also the idea used by Feng, is that, okay, this object is too bad, I cannot really define it. But instead, I can define rigorous Hamiltonians that act as upper and lower bounds for the Hamiltonian that I cannot really define. And maybe I'm able to show that there is at most one function, continuous function, that is at the same time a subsolution for the upper bound, which I for the upper bound, which I call H dagger, and a super solution for the lower bound, which I call H dagger dagger. So why do I look at this function? Because assume that you had a honest subsolution for this equation where you have the true Hamiltonian. So assume that you had this a subsolution for H, if H existed. Then, well, since H is less or equal than H dagger, this thing is larger or equal than F minus H dagger of F. So this is telling you that if you were by any chance be able to define this object and you had a subsolution for this equation, then you would automatically have a subsolution for this other equation. So working with upper and lower bounds, provided that you can show the corresponding comparison principle, should exactly capture the unique viscosity solution for this equation that we're not able to solve or even to define. So this idea has been used widely in the literature. And somehow we now introduce another simplification, or at this stage is just a hope, is that we don't have to be so clever as to define our upper bound on a large class of test functions. We will just look at a very, very specific class of test functions, which are test functions containing only d-square objects. So the test functions I'm looking at right now, I fix an element of my metric space, and I look at the function that computes the square distance from this element, plus a constant. And okay, I can also multiply the square distance by a positive constant. So why do I look at these functions? There is a specific reason. The reason is that if you take the classical comparison principle proof for Hamilton-Jacobi equations on RD, one way of doing it is through this doubling of variables method. And when you use this method, the only test functions that you need to use have exactly this form. So somehow here we are really hoping for a lot, because we are hoping to be able to be able to work only with a very, very small domain for our Hamiltonian, but still be able to establish uniqueness. Okay. Okay. Now let me discuss a little bit gradient flows in EVI form and why these are related to the equation that we're looking at. Okay, of course, as you are probably all aware of, given my energy functional E, at least at the formal level, the gradient flow starting from pi should be just the solution of this equation. But okay, for the exact same reason that made my Hamilton-Jacobi equation complicated, somehow writing this equation directly this way may not always be possible. So that you use, people typically use some more implicit characterization of gradient flows. Namely, you define a gradient flow through a set of inequalities. And one possible way of doing this is to use the so-called EVI characterization. So what is this EVI characterization? So if I fix some k in R and starting point for my gradient flow that I call pi, a solution of the EVIK inequality is nothing but a continuous curve from 0 plus infinity into the domain of my energy that satisfies a certain inequality, which is the following. So as soon as I fix a point with finite energy and I differentiate the distance squared between my curve and this point, this is less or equal than the difference between the entropies minus a term, which is minus k over 2 times the distance squared between the curve and the point. So once again, this might appear a bit cumbersome at first sight, but if you toy around a little bit with this equation on RD, and you translate all these concepts into RD, this inequality is an easy consequence of the convexity, of the K convexity of your energy functional E. And the surprising thing is that this inequality indeed characterizes the gradient flow. So there is at most one curve satisfying this under suitable assumptions, and this curve is precisely the gradient. So what is the relation between this notion of gradient flow and the equation I'm looking at? The relation is that the bad term in my equation, so the cross product between the gradient of the energy and the gradient of my test function f, as soon as f is exactly of the form that I've chosen here, then I can relate my bad term to the derivative of f along the gradient flow evaluated at time 0. So this is once again formal, but it's going to be helpful to construct my my upper and lower bounds. Maybe I can spend some time on explaining this a little bit. This relation a little bit. So I put once again myself in the simplest possible setting. So my metric space is just RT. Then of course the distance is just the Euclidean distance. So now a test function that has the form I like has the following form. Is just the distance from a given point y squared, and maybe I put 1/2 to have a nice formula for the gradient. Well, it's obvious that the gradient of f is nothing but x minus y. So this expression here would be nothing but, when you evaluate it at a certain x, is nothing but minus the gradient of your energy at x inner product with x minus y. Okay. Now, if you evaluate this expression, so ST is nothing but the solution of this equation, and you start from 0. So this expression here would end up being, so this one, nothing but s dot t pi at time 0 times the derivative, so the gradient of f, which is once again x minus y. So here I'm using standard chain rule, but this thing here is nothing but minus the gradient of the energy calculated at x times x minus y, and this is because my s is solving the gradient flow equation. Okay, all this was to say that the bed term in my Hamilton-Jacobi relates pretty much to the behavior of my test function along the gradient flow. And now I guess maybe you already feel how I'm going to define my upper and lower bounds for the Hamiltonian. Oops, sorry. This has spoiled all the... because now, so the formal action of the Hamiltonian is this one on a test function of the form I like. So some constant time square distance object plus another constant. So I have two terms. First, I have the gradient of the square distance. I take the norm of this and I square it once again. But of course, this is nothing but the distance square itself. Once again, if I do the analogy with RD, and I use the fact that the gradient with respect to x of this object is nothing but x minus y. When I evaluate it at x, then I immediately see that this chunk is nothing but a square over 2 d squared pi rho. And this term here, by now I know that this is equal to a times the derivative of d square along the gradient flow. At time t equal to 0. But for this expression, I have my EVI. So this is exactly the expression that EVI takes care of. So I can just copy paste the upper bound of EVI in order to get my upper bound here. So here I get plus A that multiplies the energy of rho minus the energy of pi minus k over 2 times the square distance between pi and rho. Okay. So what is the advantage of this? Okay, first of all, this is a lesser equal because I now have an upper bound. The lesser equal comes from the fact that EVI also has a lesser. So the first advantage is that this is completely rigorous. So the right-hand side here, provided the energy of rho is finite. Okay, it might be minus infinity. The energy of pi is not finite, but as a function, it's perfectly well defined. Whereas the inner product between the gradients is not. So actually, I can use it to define an Hamiltonian, and that's exactly the first thing that we try to do. So we said our Hamiltonian, when we view it as an operator, is just the set of pairs Fg, where F is my test function here, and G is exactly the upper bound that I have obtained. And if you work in the same way, you can also produce a lower bound. So now that you have, so the lower bound would be called H dagger. So now that you have upper and lower bounds, you can define the notion of viscosity solutions with respect to your upper and lower bounds, and you can hope to be able to show that you have the comparison principle. So there is only one function that is at the same time a subsolution and a super solution. So now the question is, can you really do that? Is your upper bound strong enough in order to allow you to do this? So I anticipate the answer. The answer will be no, but let me explain you a little bit why the answer is no. So since we adopted this somehow geometric viewpoint, what we try to do is to imitate the usual proof of the comparison principle for Hamilton-Jacobi equations. Namely, we try to follow what Feng and their co-authors have done. So if you do so, you run into a first problem that is obvious, that the metric balls in our big spaces are not compact. So this is a typical problem in three-dimensional Hamilton-Jacobi equation. And a typical remedy is to to make use of the so-called Ekelund principle or perturbed optimization principle in order to produce semi-optimal points for certain functionals over balls that have good properties. So I will not give the details. When you apply the Ekelund principle, then you need to choose a certain divergence function. So Ekelund, the application of Ekelund comes with the choice of a certain divergence function. The most natural choice would be to pick the distance itself, to pick d. So to apply Ekelund with t, because this would give you a very good control on your semi-optimal points. Now, the big problem that you run into is that d is not Lipschitz along the gradient flow. So if you think in terms of the Wasserstein distance, the Wasserstein distance is not a Lipschitz function along the gradient flow. So if you take the function that maps t into the distance of sp t from a certain point, well, this function is not Lipschitz, even if your energy functional is nice and convex. And of course, you may say, okay, who cares? The problem is that we really needed a Lipschitz estimate of this type in order for the proof to work. So we said, okay, we need to change the divergence. So instead, we need to apply Ekelund, but we need to throw away our bad distance d. We need to come up with something else. So actually, at this point, it is plausible to think that the fact that we needed something that was Lipschitz along the gradient flow was something that was specifically dependent from the proof strategy that we chose. But actually, not really. So the same problem had been encountered before by many other people dealing with Hamilton-Jacobi equations. And they come up in finite dimensional context with a very clever workaround for this problem. So somebody called Tataru in '92 invented this object, which is called the Tataru distance. Actually, it's not really a distance because it's not symmetric in its argument, but it still satisfies the triangular inequality. So invented this distance exactly to solve the same kind of problems that I have explained a little bit before. He was trying to establish comparison principle for Hamilton-Jacobi equations. He had some issues with the behavior of d along the gradient flow, so he invented this distance. And then some other people used it once again to deal with Hamilton-Jacobi equations. So how does the Tataru distance work? So you have your pi and you have your rho. And now here is a very sketchy representation of the gradient flow starting from rho. So the Tataru distance is the following thing. You are allowed to choose any point in the gradient flow. You compute the distance from pi to your point. And the price for going t seconds along the gradient flow, the price you have to pay for doing this is t. So this is what you pay for choosing a point which is t seconds along the gradient flow, and the Tataru distance is the optimal choice among all the possible choices that you have. So you take the best time so that the cost that you pay. Sorry, you take the time so that the cost that you pay is minimal. Of course, if you set t equal to 0, then this expression here is exactly the distance. So the Tataru distance is always an improvement, so it's always smaller than the classical, than the base metric, than the metric of your metric space. And this is an interesting property. Actually, it's not only smaller, it's Lipschitz with respect to the base metric, but I don't want to give the details here. Moreover, it has the key property that it's Lipschitz along the gradient flow. This is exactly what was missing before. So this was very good news for us when we learned about this distance. Is it over? No, because now we have learned that we have to use the Tataru distance, but we have now to include the Tataru distance in the test functions and to compute new upper and lower bounds for the richer test functions that not only include a term coming from the distance square, but also include a term coming from the Tataru distance. So now we have to start all over again with upper and lower bounds for this richer class of test functions. Now, of course, I don't want to give you the details. So there are a bunch of terms when you try to apply your formal Hamiltonian to the new F that you can treat with AVI exactly as I showed you before. The terms where you have to now be more careful are the terms that involve this new Tataru distance. How do you deal with them? Well, as soon as you have to control the gradient of the Tataru distance, you use the fact that the Tataru distance is Lipschitz, so the norm of its gradient is always smaller or equal than 1. And then when you have to pair the gradient of the Tataru distance with the gradient of the energy, well, there you use the fact that the Tataru distance is Lipschitz along the gradient flow. And then you also have your bound for this term. So I recall you that this term and this term are exactly the same thing when F is the Tataru distance. So if you use these two ingredients, so Lipschitzianity with respect to the metric and the Lipschitzianity along the gradient flow, you can once again come up with a formal upper bound, with a rigorous upper bound of your formal Hamiltonian, which looks a bit uglier than before, but not too bad. So let me just comment a little bit. These are the terms that come from the quadratic part of the Hamiltonian, and these are the terms that come from the gradient of the energy times the gradient of the test function. And the terms containing a B, of course, are the one issued by the Tataru distance. Okay, so now if I call G the upper bound, I have another definition for upper and lower bounds. Okay. And I can hope now to work and establish a uniqueness of viscosity solutions. And actually, this is what we managed to do so far. So we should be at the finishing touches of the paper, but okay, one never knows. So I don't want to give you the full statement because it might be a bit heavy to read. Essentially, the message I want to convey is that we can prove viscosity solutions assuming for the equation that I showed you, assuming essentially that you have a complete metric space, the energy functional is lower semi-continuous, it admits an AVI gradient flow for some k that could even be negative, and that the variations of E can be controlled with the metric slope along nice directions. So what does this mean? That maybe E has a very wide variations if you don't look, if you look in a specific direction, but there is a nice set of directions along which E, the variations of E can be controlled with the metric slope. So this is So this requirement is a weaker form of the fact that E is differentiable. If E was differentiable, this is always satisfied. Of course, our functions are not differentiable, but still they admit directional derivatives along nice directions, and essentially admitting the directional derivatives along nice directions is exactly what this is telling you. So maybe I should have written that E has directional derivatives. Along nice directions. And of course, the nice directions, you have to work them out, find them example by example. I just wanted to give you one example of application of this theorem, which is the one that motivated us. So if you take the Wasserstein space, so X is the space of probability measures over RD, and D is just the Wasserstein distance, and you take any energy functional satisfying the Mekan condition, then our theorem would apply. But here, okay, here I put an example of the example. So this is probably the thing that motivated us. So we just wanted to work with the mean field version of the Schrödinger problem. So we have our entropy plus interaction energy. But of course, the theorem would work for any function that satisfies the Mekan condition. Okay, I think this is pretty much all what I wanted to tell you. So thank you very much for having listened.
So, any questions? From the, okay. Leonardo.
So I got kind of confused because you showed us the naive construction of the upper Hamiltonian, right?
Yep.
Using EVI, and then you told us, oh yeah, and then the lower bound is done similarly, but EVI is a one-sided inequality, so you cannot use it twice in two different. I mean, something has to go wrong. You cheated, right?
No, I didn't.
No,
I didn't. I mean, yes and no.
I mean, the construction cannot be similar. It has to be different, no?
Yes. No, it's exactly the same one. But the thing is that to construct the lower bound, so to construct the upper bound, I ask A to be positive. To construct the lower bound, I ask A to be negative. So.
Because A is also in front of the. I see.
Yeah,
I see. Okay.
So of course it's a bit of cheating, but okay. The good message that it's enough. It's enough to give you uniqueness. So that's the.
Right. I see.
Okay.
Wow. Yeah, that's cheating. I'm just kidding. Thank you.
Yeah. That's.
So other questions from the chat? Emeric, are you sure? No? Cristiano was waiting for you.
Well, this is not a question I expect you to have an answer. So, but it's completely open, as you will see. So what you use is especially the square of distance, and it might happen that with jumps or with things like branching processes, for instance, as Emeric is looking at, Emeric and Hugo, we arrive with something different that a square. Do you think that your way of tackling the problem could be extended in such a general setting, which I'm not able to define clearly?
Yes. Okay, of course. So I should not exaggerate, but there is reasonable hope. Actually, this methodology developed by Feng applies to jump processes. The thing is that in that case, you maybe do not have EVI. So the proofs will not be as geometrical as the ones that we try to develop. But essentially, what we use of EVI, so no. Okay, Christian, you do probability. So the gradient flow is just the Markov chain or the jump processes started at a given measure. And EVI is telling you that the functional is convex. And for a probabilist, this is just telling you that the Markov process has good mixing properties, has good properties in terms of convergence to equilibrium. So essentially, if you replace EVI with all the good theorems that you can prove about how fast your process converges to equilibrium, you have hope to carry out the same method. For the branching case, well, one should see. I cannot, yeah, I don't know. This I don't really know.
Okay, it is okay. So if there are no more questions, I think that we can thank again Giovanni for this amazing talk.
Thank you very much.
And we can switch to the next speaker.
Yeah. So as usual, just a couple minutes before we move. Pierre. Oh, sorry. First thing I should just a second.